good afternoon. Now we are going to cover the second part of the drop inlet spillway design. Now we are how the spillway designs takes place. So, this is the part 1 of the spillway design. So, the drop inlet spillway design has all three components: the hydrologic design, hydraulic design and the structural design. So, we mainly focus on the hydrologic and the hydraulic part. So, first we are going to discuss about the hydrologic design, and that will be followed by hydraulic part. So, now hydrologic design, what we do here, it consists of determining peak runoff rate, which that is expected peak runoff rate, we design that, and then the second one, inflow hydrograph. So, outflows won't be same as the inflow like in drop structure or the chute spillway structure. So, that is why we have to design both the expected runoff, the peak runoff and the inflow hydrograph. Now, coming to hydraulic design. Hydraulic design consists of design of the earthen dam and design of pipe spillway. So, making a base of these two design, our next steps will go forward. So, now coming to the design of earthen dam, it consists of all design steps, that is hydrologic design, hydraulic and structural design as any kind of hydraulic structure. Now, coming to how we can make a design of the earthen dam. So, the upstream and the downstream side slope is commonly used in earth dam at a 3:1 or 2:1 slope, and the width in general varies with the height. The minimum top width should be equal to 1.8 meter for around a height of 3.5 meter. When the top width of the dam is used as a road, then it should be kept between 2.5 to 3 meter. In addition, there should also be added 30 centimeter additional top width for each 60 centimeter dam height. Now, to combat the safety against topping, 5% more height should be added as a settling allowance, and it should kept as 60 centimeter as a freeboard, and the bottom width of the dam is calculated on the basis of side slopes and its height. The bottom width should match the length of the conduit, and the side slope of the dam should be protected against erosion. So, protection against erosion is achieved by making a riprap or using heavy gravel or rocks when upstream side slope is eroded by wave action from the downstream water. The downstream side slope is not in generally affected by wave action, hence the vegetation can be grown to protect this side. Now, coming to design of the pipe spillway. In drop inlet spillway, a pipe spillway has a vertical section towards the upstream face of the dam. So, this vertical section is called as a riser, and this is connected to conduit passing through dam. The top of the riser may be raised up to a desired height for providing grade to conduit and protecting gully head. Now, to follow hydraulic design of the spillway, the type of flow occur in the conduit should also be considered. So, now this is, you can see a typical discharge characteristic curve of drop inlet spillway. So, here the first part is where flow prevails, and the second part the pipe or orifice flow prevails. So, this is the wear force, and here an intersection point is located in between two. Now, design of the pipe spillway. Here the type of spillway depends on the size of the watershed and condition of proposed site for construction. Now, the type of spillway depends upon the watershed area, how large is the watershed. So, if the watershed area is less than 4 hectares, generally vegetative spillways are provided in case of small spillway structure. But in case of medium watershed, like here it is listed between 4 to 12 hectares, combination of mechanical and vegetative spillway is to be provided. And where the spillway structure is little bit larger, that is between more than 12 hectares, mechanical spillway structure is to be provided to withstand the load of huge capacity of water. Now, coming to hydraulic design. So, here we have to consider the friction loss in the pipe and other kind of losses. So, this is in general it is taken from the flow through conduit or the pipe flow. So, as you know, when the water is flowing through the pipe, it is in general governed by the Darcy's law, and loss of head due to friction is computed can be using Darcy's law. So, this is the head loss due to friction. So, 4 FL V square divided by 2 GD, where HF is the head loss due to friction, L is the length of the pipe, D is the diameter, V is the velocity of the flow, and F is the coefficient of the friction. Now, coming to the friction factor for different pipe structures. So, different friction factor is already tabulated. So, for the pipe material, if it is aluminum material, the friction factor is 0.34. When aluminum is coated with steel, it is 0.25, and for the concrete structure it is 0.03, and the steel pipe it is again 0.23. So, as you can see from this table, for the concrete structure the friction factor is quite less. However, for metal or the aluminum structure, the steel pipe structure, the friction factor is quite high. Now, coming to the neutral or the natural slope. It is a hydraulic slope in which head loss due to friction is equal to the head loss due to elevation change in the conduit. So, it is given by a sine of the angle that conduit makes with the horizontal. So, here it is a function of friction head loss over the length L. So, sin theta is the function of HF divided by L. Now, as you know, the coefficient of contraction. So, when the pipe flow prevails, so HF is Kc, where Kc is the coefficient of contraction, V square by upon 2 G, L is the length of the pipe. So, now, sin theta can be a function of this one Kc, so where LL gets cancelled. So, here the sin theta is HF by L. So, now the equation for HF is Kc V square by 2 G. So, where Kc is the coefficient of contraction when the pipe flow prevails, L divided by L. So, here LL get cancelled. So, sin theta is nothing but Kc V square upon 2 G. Since theta is very small, we can also say that Sn is a function of the tan theta and Kc, and then 1 minus Kc V square by 2 G. So, this equation we can derive from this. So, after calculating the natural slope, the conduit capacity for different flow conditions can be computed. So, here, three different conditions are plotted. So, here when Sn is when the natural slope is less than the slope of the channel. So, the free outflow or the pipe flow prevails. When the opposite is true, so when the slope is greater than the natural slope, partly full or free outfall orifice flow condition prevails. And when these slopes are equal, so full outfall submerged pipe flow condition prevails. Now, coming to case 1, in drop inlet spillway, pipe flow will prevail and outlet is under submerged condition when the slope of the pipe is less than Sn. So, the discharge capacity in that case is given by this equation. where it is a function of area and h and couple of coefficients. So, where L is the length of the pipe, K e is the coefficient due to head loss at the entrance and K c is the coefficient due to frictional head loss in the pipe, where it is a function of pipe diameter and the resistance coefficient. Values of K c can be determined from standard graphs or tables. So, this is the coefficient of head loss for circular conduit, where these is a function of internal diameter of the conduit at different n, or the Manning's roughness coefficient. So, this is a relationship between head loss coefficient and internal diameter of the conduit. Case 2, if the pipe is laid at a greater slope than S n. So, this is the case 2 condition, where S is greater than S n. So, the entrance condition will control the discharge in this case, and in this case the discharge through inlet wear is given by the equation of wear, the flow through the equation wear. So, where C d is the coefficient of discharge, L is the crest length of a straight wear or the sum of length of 3 sides of the box inlet, and H is nothing but energy head of water over the crest. The discharge characteristics of the drop are then prepared, and the stage versus storage capacity curves are also prepared in this case. So, using the inflow hydrograph, storage capacity curve and the discharge characteristics of the structure, the outflow hydrograph of the structure is then developed. This is the flood routing steps. And lastly, for the design Strom hydrograph is selected, the storage capacity and the discharge characteristics of the structure is then selected, should be in such a way that temporary storage will not exceed the design depth of the embankment. So, some of the coming to some of the important features, the outlet of the drop inlet spillway is placed slightly above the elevation of the grade established below the structure. Second, the conduit pipe is extended about 2.5 meter below the toe of the dam and is supported by concrete pier. The support is placed around at a 2 to 2.5 meter from the end of the pipe to protect it from the score hole that will form. The straight apron type and the stealing basin type outlets are in general adopted for in the case of drop inlet spillway. Now, we are going to solve a small problem based on the design steps I have taken. So, determine the discharge capacity of an underground concrete conduit of 15 centimeter diameter. The length of the pipeline is kept as 200 meters, and the difference of elevation between the water levels at the inlet of the structure and downstream of the structure is 2.5 meter. So, this information, the last information will be used for calculating the slope of the structure, and take f 0.009 for concrete pipe for a given diameter. So, here we first calculate the velocity of flow using the formula. So, this formula is already covered in the beginning, the velocity of the flow through the pipe. So, this is the Darcy's formula, as you can see here. So, using that, we first calculate the velocity of flow in unit of meter per second. Now, once we know the velocity of flow, we calculate the cross sectional area of the pipe. So, since the pipe is assumed as circular, the cross sectional area will be a function of diameter of this pipe, and pi d square by 4. So, here comes the cross sectional area. And now, the discharge capacity is nothing but a function of the cross sectional area and the velocity, which is then we multiplied here, we are getting the discharge capacity of the pipe. That is it. Thank you.